Good. So for this session, we have Saso Grozdanov. He will be telling us about the structure of classical hydrodynamics and spectra of holographic QFTs. So please take it away.
Thank you. Maybe just 1 second to hide this. Okay, floating meeting controls, whatever they are. Okay, perfect. Hopefully you can hear me all right. Yeah, just stop me if there's something. All right, thank you very much. Thank you for the invitation to this conference workshop. I am very sorry that I cannot be there. It was sort of out of my control due to various circumstances. But okay, at least we do this over Zoom, and hopefully, you know, soon I can come to Bangalore and see your amazing institute. So the title of my talk is The Structure of Classical Hydrodynamics and Spectra of Holographic Quantum Field Theories. So let me start with sort of the general, motivation for why I do these kinds of things. So I am generally interested in thermal things, in transport, and in particular, thermal field theories, which describe very interesting states of matter, like plasmas, neutron stars, quark-gluon plasma. And then, of course, through the help of holographic duality, which I don't assume that all of you know there because it's a Hydro workshop to some degree, a lot of these questions about matter that is strongly coupled, which would be otherwise very difficult to access, can be translated to simple questions in black holes. And black holes you can also think of as thermal states. So nothing I say will really require any knowledge of holography, but often because holography is the easiest way to calculate anything, I will just naturally be using holographic examples. One thing to say, it's particularly useful because for certain types of quantum field theories, not the kinds that we know exist, but hopefully close enough to things like QCD, holography is really good because of this strong weak duality. So it allows you to compute strongly coupled phenomena in terms of weakly coupled gravity. And in fact, if you go to quantum field theories at large N, which is typically what I'll be doing because anything else is extremely difficult to do in terms of transport, and especially at the level of exactness of the statement that I would like, the nice thing there is that these translate to essentially a semi-classical limit of gravity, of quantum gravity, which is just classical gravity. So for all intents and purposes, you can ask certain questions about quantum field theories, which are strongly interacting. They're toy models of various things, and you can translate these problems into the computation of black holes. Now, I will be discussing, in particular, thermal spectra and transport. So what do I mean by thermal spectrum? So what I really mean is I have a system, I kick it, and according to this equation 1, which is the equation of linear transport, of linear response, what this tells me is that the expectation of a quantum operator given some source that kicks the system is encoded in the 2-point function. It's encoded in the retarded 2-point function of the observable operators that I'm interested in. And in particular, for most of the things that I'll be discussing, these 2-point functions will have very nice structure. In fact, they will have, in momentum space, which is typically where I'll be working, such correlation functions will have, of course, some numerator and some denominator. And the denominator, the analytic structure of this will be simple poles. This is very nice. So in the time domain, this translates to just an infinite number of these types of relaxation terms. In the frequency space, which is typically where I'll be working, these are poles of correlators. So the poles of correlators give you the physical relaxation of your system. And yeah, so my assumption for most of what I'll do is the following. So I'll be plotting these types of diagrams that you see here on the bottom left. This is the analytic structure of my retarded correlation function, which encodes the transport and the response. And given some fixed momentum q, the wave vector q, and given some temperature or whatever other quantities determine my state, these will be simple poles in the complexified frequency plane. Okay, so wherever I will put a dot, these will be the zeros of the denominator, so the zeros of A. Okay. Now, the nice thing about holography is that these things for strongly coupled thermal quantum field theories can actually be computed from much easier spectra of higher dimensional black holes. So these spectra of black holes are called the quasi-normal modes, and we can compute them. Okay. Now, so the outline of the talk. So first, I want to talk about hydrodynamics. Then I want to talk about some very general properties of the spectra of thermal field theories. And in the end, I want to tell you about sort of how magically through the help of complex analysis and some mathematical methods, we can basically understand everything, at least in principle, about the spectra of quantum field theories just by doing hydrodynamics and analytic continuations. So let's start with hydrodynamics. So what is hydrodynamics? I'm sure the room is full of experts. For me, it's a low energy theory of conserved charges. It's a theory that encodes various conservation laws like energy, momentum, charge, whatever you might have. And what is really crucial is that's a theory in what we call local thermal equilibrium, or something that we nowadays maybe call the local KMS relation. So it's encoding, or it's expressing the most low energy part of your spectrum of the theory, which means in this complex frequency plane, it's to do with the physics of the poles, which are close to the origin, because low frequencies are low energies. So basically, it's dominating the part near to the real axis in the spectrum. So from the point of view of the old sort of style of equations of motion, what classical hydrodynamics is, it's a series expansion. So it's an infinite series expansion in terms of some kind of hydrodynamic variables, which, in a neutral fluid, it's fine to take the velocity field, some out of equilibrium generalization of temperature. You assume that their derivatives are small. And in principle, you're supposed to take your conserved operators like the energy momentum tensor. So everything I do will be relativistic, but one can just take a non-relativistic limit at the end if you wish. These are expressed in terms of counting of the number of derivatives on these fields. And in principle, you can write down an infinite series in higher and higher derivatives. And this translates in the old language into counting of, let's say, zeroth order hydro, which is ideal hydro. And this will give rise to the Euler equations once you impose the conservation of energy and momentum. If you include first order coefficients, then you will have Navier-Stokes equations. But nobody tell you that this is the place where you should stop. So in classical hydrodynamics, in principle, you should go to an infinite series of such corrections. Now, for me, what will be most interesting, again, is linear response. So I will be looking at the decomposition of my velocity and temperature in terms of Fourier mode. So something like e to the minus I omega t plus iqz. And the nice thing about solving for the conservation law, the Navier-Stokes equations generalized to all orders, is that at the end of the day, what you recover are what are called dispersion relations. These are these functions omega as a function of q. And the feature of hydrodynamics is that you can write them as infinite series. This is stemming from the fact that you can write down an expansion in infinite powers of derivatives. So this will then, once you solve these equations, it will translate into the frequency being expressed as an infinite series in powers of q. Okay. Now, simple examples of such things.
Can I ask a question, please?
Sure.
Are you talking about relativistic hydro, or does that include non-relativistic case as well?
It's the same. It doesn't make any difference. What happens in non-relativistic cases is that just often these higher derivative terms might be suppressed by 1 over c. But otherwise, this is the same as in non-relativistic theory. There's nothing special here.
I see. I was a bit worried because the dispersion relation. You don't have like light cone, like causality in non-relativistic theories, and you could have like low energy modes, which have very large wave number and stuff. So I was wondering.
Yes, then this introduces an entire family of problems, which I will touch upon right now. Very good point.
Thank you. Thank you. Okay.
So exactly. So let's say that you truncate your series at first order at the Navier-Stokes level. The typical two dispersion relations which you get will be, you can see them at the bottom. I don't know if you can see my cursor, diffusion and sound. So diffusion goes as omega is equal to minus I. D is the diffusion constant, which will depend on the transport coefficients of the theory, on the microscopics. It goes as q squared. So as was just pointed out, of course, for large q, this violates causality. It violates the assumptions of relativity. Now, in non-relativistic physics, this is not a problem, but in relativistic physics, which, does underpin our reality because we live in a relativistic world, this is a problem. So what happens is that actually it's always this other infinite series of corrections which will correct you to get back to respecting causality and the speed of light cone for large Q, with a little bit of a caveat to be discussed later. So diffusion has a term. So if you just truncate, you will get, for diffusion, you'll just have a term that goes as Q squared. For sound, you'll have a term which is real, which goes as Q. This is the speed of sound. And there's some attenuation, okay? So of course, the thermal state by itself breaks Lorentz invariance, it breaks boosts. So at the end of the day, these things you compute are anyhow don't look relativistic, even though they come from a relativistic theory. So, the thermal state by itself breaks boosts, and therefore it breaks relativity. Good. So sort of something very new that I don't have time to really go into details is that this type of classical hydrodynamics is extremely full of ambiguities. And the reason for this, which was known for a long time, is that there's no a priori out of equilibrium definition of your temperature, for example. You can only define temperature and equilibrium. So this gives rise to ambiguity. So one type of such ambiguities are known as frame transformations or frame dependence, where you can change your temperature field up to subleading derivatives. For example, this then results in, I don't know, Eckert frame or Landau frame or whatever. So generically, you can have any kind of frame you want, but there's an ambiguity, okay? You will get different equations. Now, there's actually also another type of ambiguity, which I don't think people appreciated before. Well, they did, but maybe it wasn't formulated in such a way. So what people also do routinely in hydrodynamics is they solve the zeroth order equations and insert them into first order equation in order to simplify them, and then go on like this. So this what we call now is our on-shell transformation. So basically you're plugging in lower order equations of motion into higher order equations of motion in order to simplify them. And actually what we showed recently with my PhD student, this is just from November, it's a little bit of a technical paper, but I can explain just the point here. So basically what happens is you can think of these both types of transformations as giving you families of hydrodynamic theories, essentially equivalence classes, which all have different transport coefficients. There are lots of transport coefficients at high orders, but at the end of the day, all of their physics will be the same. So you have these infinite sets of equivalence classes of hydro theories, which you can relate to each other. It's a little bit like a gauge theory of hydrodynamics, although I don't want to call it this because these are really field redefinitions, but we can make this very precise. And in fact, each type of these transformations, the frame transformations and the on-shell transformations, give rise to an actual algebraic structure, which is so you get two nilpotent Lie group structures, one multiplying from the left and one multiplying from the right. So all this mathematics aside, what the result of this is that you can understand very precisely what this does to correlation functions. So in fact, with these weird transformations, think of it of going from Landau to Eckart to an infinite family of such frames. What your correlation function what will happen under this transformation is that whenever you have a hydrodynamic theory truncated at finite order, it's like taking a correlator and multiplying the numerator and the denominator with the same polynomial in omega and q. So you can actually arbitrarily change the physical the poles of the theory, and by this you can use these tricks to stabilize the theory and make it causal and stable. So this was noticed by these people like Benfica, Desconzi, Noronha, and Kofton. There's something called the BDNK formulation, which even allows you to put first order hydrodynamic equations into a causal form so that you can solve them on a computer. Of course, it doesn't change the physics because the physics is still in the low energy part of the spectrum. It just adds arbitrary high energy modes to stabilize your equation. So you can then solve it on a computer. And in fact, we show that these gapped modes that you can add are arbitrary. You can do whatever you want, but within this group theoretical structure, there are certain group invariants which keep the physics that is actually there. So for example, the dispersion relations of the hydro modes remain invariant. And so this is something very, very new. I just wanted to point this out because we kind of now understand this much better than at least I did in the past. And now I want to go to the next aspect of hydrodynamics, which has been recently very popular. So everything I said so far is formulated at the level of equations. Now, as high energy theorists, we really, really want an action. So there's been this sort of a long-standing issue of how does one write down an action for the hydro theory, because these things are dissipative. So, it's kind of difficult. So this has a very long history. So in the past, it started, I think, from Lautweiler, who said, this was sort of hydro formulated in terms of some kind of massless scalars and a theory that looks like a sigma model. There was a sort of a resurgence of these ideas in 2012 by Dubovsky, Hui, Lam Hui, and Nicolis and Damson. And then there was sort of the outstanding problem of how you make this dissipative. So what we showed in 2013 with Janos Poloni is that, well, what you should really do is take your fields and double them, put them on a Schwinger-Keldysh contour, and just work with doubled fields. And what will, then at the end of the day, your action looks like a doubled copy of the same fields. You have some structure that looks like S of phi 1 minus S of phi 2. And this structure of Schwinger-Keldysh theory allows you to couple these contours. There's a time contour going forward and backwards. I'm sure that people have by now sort of become sort of familiar with this to some extent. So what is crucial here is this term that couples the two contours. It's called the influence functional, and it has some interesting constraints that arise from unitarity, essentially. It has to have some complex properties. So this was then, generalized to made very, very systematic from the point of view of Stückelberg fields. For example, in various works, there's the MIT group and the group around Mukund Rangamani, Loganayagam, Hale, and various other people have worked on this. And this has been improved a great deal. And for example, one of the really nice things about those works is that people finally really understood what entropy currents should be. I think that was the main contribution of all this. So that was very, very nice.
Hello.
And now, yes, please.
So what is the motivation behind this formalism? This doubling of the scalars?
You want the theory, the equations of motion, to have dissipation. If you start with a standard field theory on a contour, you will never be able to produce a dissipative term from a single field, because that will just be a total derivative in the Lagrangian, and it never gives you anything in the equations of motion. That was the motivation why we introduced this.
Thank you.
Yeah, very good. Thank you for the question. Very important. Yeah. Good. So now for the motivation, why on earth you would want an effective field theory of hydrodynamics, I can show. I will show you an example. So another recent thing that I wanted to show you as well is that sort of for years we were always saying, well, there's going to be this influence functional. So one of the interesting questions that I had also in 2025 with my other student, Giorgio Frangi in Edinburgh, was we actually wanted to derive this influence functional from something, not just keep saying that it must be there, like what I was doing for the last 10 years. It's nice to actually see how this actually arises. It turns out that it's not that easy. So what we did for just as a simple thing was to take phi to the 4 theory, scalar phi to the 4 theory, put it at finite temperature, and do a Wilsonian RG and see what you actually need to do to get the influence functional which couples the two contours. So it can be done. This was published this year in 2025. And it's I don't want to say too much, but I would say that now we understand all sorts of sort of complicated subtleties in QFT which are necessary in order to give you an influence functional. And it really has to do with thermal field theory problems, for if there are people who are experts of this in the audience. Basically, because of infrared divergences, you have to do a resummation. You develop a thermal width of the particle, and it's really the thermal width which gives rise to these types of influence functional terms, and without them, you just don't see anything. Okay, so this is now understood. So, for example, in the phi to the 4 theory, what happens is that in the effective action, you will have a g times phi 1 to the 4, and then g bar phi 2 to the 4. Actually, this coupling g becomes complex. It's very interesting. So everything becomes complex, and there's an influence functional with a new coupling gx, which couples phi 1 and phi 2. And by unitarity constraints, which are all obeyed in this QFT that you can check explicitly, what happens is that this Gx must be 2 times the I times the imaginary part of the coupling G, and this is exactly what comes out. So, I would say that now sort of we understand much better, or at least maybe other people already understood it in the ConMat community, but certainly I now finally understand what exactly you need to actually get such an influence functional. So now forget this, no more microscopics. Let's go just to the effective field theory.
All right,
so,
just to understand. So from what diagram does it come from if you do Wilsonian RG?
It comes from, so you have a phi to the 4. You have a phi to the 4 for fields 1, and you have a phi to the 4 for fields 2, and it comes from these mixed loops.
I see.
But then this is not enough. You have to sort of do a ladder resummation of those to get rid of the infrared divergence. So actually the influence functional, the really interesting thing is it's non-perturbative. So it goes as g squared over g squared. So, it doesn't arise perturbatively in this context, at least. So you do a perturbative calculation, then the resummation introduces this, I didn't want to go into the details, this kappa called the thermal width, which also scales as g squared. And then there's the perturbative over the thermal width, and they cancel out. So it's actually, it's an order 1 non-perturbative correction to the effective action. Okay?
I see. Thank you.
Yeah.
Saso, so by this resummation, you mean like a Dyson-Stringer kind of resummation?
Yeah, beta salpeter, I guess I would call it. But basically, that's that. Yeah.
Okay.
Yeah, that's right. Yeah, exactly, precisely.
Thanks.
Yeah, it's these sort of thermal field theory is very irritating and very difficult, and it's mostly because you have all these infrared problems and you have to resum stuff, and the perturbation theory itself stops being analytic because there's a thermal mass generated which goes as a square root of the coupling. So there's a lot of trouble that you have to go through.
Yeah.
Yeah. Anyway, yeah, I'm sure you know all this. So I was happy to see how this actually arises. So now forget this. So let's go back to our EFT and just look at a simple example of diffusion. Okay. So and this is now mostly following this language, I would say, of Hong Liu and the MIT group. It can be done in other languages. I would say this one is the closest to the language I was using before, so I'm most used to it. So what do you do, right? So you write down a generating function and you impose some sort of a symmetry. So I don't want to go into the details, but basically you have to integrate in a set of fields, which are called the Stuckelberg fields, which impose conservation, in this case, of a current, because I want to work with diffusion. So whatever, there's some well-defined procedure. You go through this, it's not very difficult. And what at the end of the day, you can write down is some action. So this is now a quadratic action in terms of the Stuckelberg fields. It couples the two contours together. So this is really the simplest thing you could do. This is a quadratic action in the Stuckelbergs, and it goes up to a first derivative. Okay. So first derivative on B, and then of course B's naturally already include derivatives. The details are not so important. This theory, it's an EFT, and you can compute stuff with it. You can compute correlation functions, and you will find that exactly the correlator computed from this will have a pole. And the pole, unsurprisingly, is a diffusive pole. So there's a pole in the correlator at omega is equal to minus I dq squared, where d would then be related by the Einstein relation to the conductivity and the susceptibility. So this was then generalized actually to a full nonlinear theory. And the interesting thing is that you can do this. It was first sort of looked at in this paper by Chen Lin, De La Cretas, and Hartnell. And then we generalized it to a completely nonlinear theory so that we could see what comes out of this. And the nice thing is that, you have a theory of diffusion, and then you start treating it as really a QFT. Okay? I guess it's a stochastic field theory because H bar is still small. But at the end of the day, this is really a QFT with, all the nonlinear terms, and you can treat it with all the Feynman diagrams, and you can compute things. So there's some very nice predictions, actually. So what this EFT, if you take it seriously, predicts is that, okay, well, the dispersion relations will become non-analytic. So this omega is equal to minus I dq squared will have all sorts of non-analytic terms that come with logs. Okay, these in the old language, these are basically long time tails. So these are the non-analyticities that are introduced into the classical hydro theory from the long time tails. Another interesting things, is that the spectrum also develops an infinite sequence of branch cuts. So there's now an infinite sequence of branch cuts that go at minus I dq squared divided by n over 2. Okay, so they're actually living more in the infrared than the hydro mode, which really kind of implies that at late times, these hydro modes can decay into all sorts of other modes. And one other particularly nice prediction of this, which was already seen at one loop by this paper by Chenlin, De La Cretas, and Hartnell, is that in some dimension, the diffusive pole is predicted to split into two. So the prediction of this EFT would be that the diffusive pole actually develops a small propagating part. Okay, so these are predictions. I don't know if this has ever been checked in molecular simulations or things like this. If people know about this, it's unclear. But this EFT does give you some prediction. It just says that with all this higher order stochastic loops, the diffusive mode should generically also develop a small propagating part. Okay, so that's one nice thing. Now, this was the hydro part. Now I want to go to the whole spectrum of going from hydrodynamics all the way to the ultraviolet, to high energy. So first I want to ask, what do these correlators actually look like? So these correlators in QFT have typically very complicated structures. They have poles and they have cuts, all right? Now, what we know about QFT spectra is the following. So we know that at zero coupling, the correlation functions of the energy momentum tensors, these are like energy correlators or momentum correlators. At zero coupling, they have an infinite sequence of cuts. This was shown by Hartnell and Kumar in 2005. On the other hand, what holography always tells you at infinite coupling is that these are simple poles. So the correlator only have simple poles, i.e. they're meromorphic functions. Okay, so one interesting thing is that it seems that if your calculations go from the weakly coupled to strongly coupled, for example, like in kinetic theory, you will typically develop cuts. And this is not so surprising that again here in the EFT, which is a perturbative calculation of hydro, you are developing cuts and cuts and cuts and cuts, more and more of them. Now, if you do a holographic calculation and you start including 1 over the coupling constant corrections coming from supergravity, what you always find is that poles just become poles. And actually, over the years, mainly in my collaboration with Andrei Starinets in various papers, also with collaboration with other people, Nikos Kaplis, Casaldere Solana, and others, what we found is that these, the supergravity itself, so holography, black hole physics, does know how to form cuts. So what happens is that when you go from strongly coupled systems to weakly coupled systems, these poles will accumulate. They will eventually come closer and closer together. And actually what these poles, so what the correlator structure is that there's always a pole 0, pole 0, pole 0, pole 0. And in the limit, you form a cut, okay? So we see even numerically that, as you go towards weak coupling, and remember, these are sort of, finite correction. So we don't have, of course, the full resummation of supergravity because that would be called string theory and we don't know how to compute those things. We see the formation of weakly coupled physics. For example, we also see the formation, these quasi-normal modes take the role of quasi-particles and so on. They can be seen in spectral function and all sorts of interesting things. So now for the rest of my talk, I will assume, very important for everything else that I'll do, I will assume that my correlation functions are meromorphic functions, so that they're only simple poles. So there are no quantum corrections of the type of hydro, no long time tails, and no other types of probably 1 over n corrections, which are also expected to give you cuts. So they're only meromorphic. Now I want to talk about the reconstruction. Basically, what I want to tell you about is how, for such theories, if you know all the details about the hydro mode, you can actually prove that you can then also figure out all of the details about the other modes in the system, all of these other sub-leading relaxation times, if you like, in the language of hydro. So this is about reconstruction. Now, of course, I don't have too much time to go into all this. This is a long story, but basically, it started through this phenomenon of pole skipping, which I don't have time to go. Some of you know this, some of you don't. It doesn't matter. What we found is that there are special places in this complex omega and Q space where the correlator does not only have a pole, but if you tune the pole, it goes around. There are places where its residue goes to 0. So these are special places where the correlator is 0 over 0. And we initially found this in connection to quantum chaos, which is not important here. Now it's recently been shown that this is also very precisely related to entanglement wedge dynamics and things like this in holography. So what we found is that there's actually an infinite set of such points in the correlator, in the spectrum. And now, so they always lie at negative imaginary multiples of the Matsubara frequencies. So such points happen for some q, complex q, such that omega is equal to minus 2 pi t I n, with n being greater or equal to 0. There's only one special point where n is equal to minus 1, and that's the one that's related to quantum chaos, which will not be important here. Now, why is this important? So in simple holographic models, what you find is as follows. I want to go beyond low energy, and I want to see what is going on at high energies. So these infinite series, first of all, what is very important is that we were able to prove is that these are convergent series. So they have a finite radius of convergence. Okay, so that's the first nice statement, which I'll be using later. And now, for these simple cases of diffusion, if you just take Q to be larger and larger and larger, what you find is that this diffusive mode will just start here and just go down, 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 down. Okay, it will go down the imaginary axis. It will stay imaginary, which means that it will actually traverse all of the multiples of the Matsubaras, which are easy to compute from pole skipping. So these Qs at the Matsubara frequencies are actually very easy to compute. So for example, in ADS, in three-dimensional CFT, the simplest example of thermal three-dimensional CFT, you can even get it analytically. Okay. Now, so this gives you a sort of an interpolation problem. So the hydro mode goes all the way down, and you know the value of its dispersion relation at discrete number of points. And now my claim is that actually just knowing these discrete points of where it goes through the Matsubaras is sufficient in some way to reconstruct the entire dispersion relation. So how to do this, it's not very easy because typically interpolation problems don't have unique solutions unless they have some special analytic properties, like some Nevanlina pick, positive definite form, and things like this. I don't this complex analysis. So here you have none of this. There's no special thing, or at least I couldn't find it. But what we found was a little trick, which is actually very useful in the GR community, and also in atomic physics, actually. So you can imagine that instead of working in however many dimensions of a fluid, you're working in a general number of dimensions d. Now, everything simplifies in large D because forces become ultra localized. For example, Coulomb force or the gravitational force, when D goes to infinity, it becomes ultra localized. And then you can solve things exactly and do a perturbation in 1 over D. So we showed that with this trick, actually you can solve this problem, at least in principle. It's still very difficult to do, but ideologically this is possible. So I will not go into details, but what essentially happens is that the hydro series in the 1 over D expansion at higher and higher orders of D truncates. So the series becomes finite. Okay, so you have a finite series, and at higher orders in D, the series becomes longer and longer. Now, at any order of 1 over D, this mode will still go through all of the pole skipping points. So now all you really have to do is solve an interpolation problem of a finite polynomial going through an infinite number of known points. And this is something you can do. So you can use this with some extra analytic continuations to show that if you know all the pole skipping points in the 1 over D series, you can then uniquely fix the entire hydrodynamic expansion. Okay, so that's the first statement that I want to make. Now, the second statement is that once so if you have a spectrum which is sufficiently complicated, and I will tell you what sufficiently complicated means, if you know just the hydro series, the infinite series, you can then also get the dispersion relations of all the other modes by doing essentially just complex analysis. So these spectra have such nice properties, and we showed in an algorithm with my other student who recently graduated how to do this. You use a combination of some complex analysis theorems, and it works as follows. So the hydro series has a finite radius of convergence. Okay, this is my omega 0, the lowest lying mode. Now, from the structure of the series, you can figure out where it will break down. So you can use what is called the theorem of Darboux in some version to find out where it stops converging. But not only, you can also figure out with what power it will stop converging. So there'll be some branch point that happens in this complex Q plane, and you can figure out what is the order of the branch point singularity there. Now, what you know then you can take this Hydro series, you re-expand it around the branch point where something goes wrong, it stops converging, and you know that it's a Riemann surface of order 2. It always happens to be order 2. So now once you've re-expanded the series on one sheet, you know exactly how it must be re-expanded on the other sheet by theorems like the Puiseux theorem. Doesn't matter. It's basically pluses and minuses coming from square roots. So what this actually allows you in principle to do is to go from the Hydro dispersion relation and then go to the next mode, find its dispersion relation, go to the next mode, and so on by doing this. And we actually showed in some holographic examples that this can be done numerically in practice. So it's an analytic algorithm, but you can sort of execute it, order by order. It's not very practical because you would really need to know a lot of these coefficients, but in principle, this can be done. Okay, so
can I ask
now, absolutely, yeah.
So is there like symmetry behind this phenomena? Because it looks a bit like bootstrap and,
No, not that I know. So what is behind this is what in quantum mechanics people call level crossing. So basically what happens is as follows. You can think of these modes. So you can tune the modes, you go to some complex Q, and so they will dance around in the complex omega space, and at some point they will collide. So when two modes collide, if this collision is non-trivial, what will happen after that is that if you go to Q's higher than this, they can dance around and swap each other's places. So they develop a non-trivial monodromy. So basically, the two modes, which looked independent, are at that point, and after the point of collision, they're actually a part of the same spectral curve. So this is like, starting from the ground state of the quantum mechanical problem and going to the, and reconstructing the first excited state by doing level crossing. So basically, these are special points where level crossing of the modes happens. Now, these are quasi-normal modes, so they're not real, they're complex. But it's like this. It's basically, low energy modes slowly swapping places with high energy modes and having non-trivial monodromies in the complex plane. That's how this works. If there's some symmetry bootstrap-ish thing, then I don't know. Would be great. I mean, yeah, does this make sense?
Yeah, definitely. Thank you.
Thank you. Yeah, great, very important question. I don't know the answer. Would be happy to. Okay, so good. And now, sorry, I heard something.
Yeah. So when you are saying here that from the knowledge of all the pole skipping points, we can reconstruct the full hydrodynamic spectrum. Do you mean that like it is the spectrum of only one of these modes, or do you mean that if there are suppose any other non-hydro modes in the picture as well, we can reconstruct their full picture and maybe the full dispersion polynomial as well?
Good question. So yeah, I don't know. I mean, those I think yes, but you would have to find very special cues where they go through. I haven't tried that. I think you could. My feeling is that you could, but I don't know how to. I haven't really tried. So my statement was that you could do so from the pole skipping points, which are easy to compute, you can reconstruct the full dispersion relation of the Hydro mode. That we've shown how to do, even in examples. Again, it's an analytic procedure, but it's incredibly complicated. So going beyond a few orders is very, very difficult. And what you then end up with are actually transport coefficients in d dimensions. And then you have to set d to be equal to 4 or d to be equal to 3. And that actually works. Remarkably, all these things for at least the things that I was able to try, they work well and everything converges. And it actually gives you the right coefficient, sort of order by order of Hydro. So I believe that it would work. Yeah. And then the second statement is once you know the Hydro series, you can go, if the spectrum is sufficiently complicated, the formal statement is that all of the poles in the spectrum have to have places where they do level crossings with each other. If that's the case, then you can then reconstruct the entire spectrum from just the hydro mode. And actually, that is not specific to the hydro mode. Any one of them that you would know, you can reconstruct all the other ones, okay? I hope that answers the question. Good, and now another thing, which I've been sort of very excited about, and this is the last thing I want to tell you about, is another sort of extremely stringent set of constraints that we were able to find with my student Mile Verbica, who is just about to finish his PhD in Edinburgh. And we wrote 3 papers on this. And now this is called the spectral duality relation. And what this does is basically the following thing. We showed that for certain cases, if you know the spectrum of the sound channel, so of the longitudinal channel, you can also just compute from that the spectrum of the shear channel. There's a complete sort of one-to-one constraint. Even though they look different, there's again an analytical procedure. Everything is so incredibly constrained that you can do this. So this is really coming from the physics of black holes. This we would have not been able to do in any other way. And so it's actually now this is maybe the only thing that I will say about black holes. So it goes as follows. So if you take 4-dimensional black holes, which is good because that seems to be the number of dimensions that we live in. So by this holographic dictionary, 4-dimensional black holes are equal to the spectra of 3-dimensional thermal field theories. Okay, so this would be 2 plus 1. So I'll be talking about 2 plus 1 hydro now. What is remarkable is the following. So the perturbations of gravitational waves in 4D have 2 channels, the longitudinal and the transverse channel. Here, they're often called the even and the odd, or sound, or diffusive shear, whatever. So what is known as the following. So there's a very beautiful theorem that goes back to Chandrasekhar in 1975 and his wonderful book, I guess not surprising. So what he figured out was something called an isospectrality theorem, okay? So in asymptotically flat spaces, the spectra of sound and shear channels, the even and the odd channels, are equal to each other. And I think this was actually quite surprising because the problem is when you look at the equations that are supposed to give you these spectra, they look completely different. Okay, they look very, very different, and yet somehow all these modes are the same. So this is it's a beautiful result. It's called isospectrality. Now, it was not known what should happen to this when you go to anti-de Sitter. So when you go to negative cosmological constant, things look very different because now, holography is ADS-CFT. So these black holes that we deal with are really in spaces with a negative cosmological constant, which has a boundary. And this changes the game completely. So now what we were able to prove is an equivalent to the isospectrality theorem, which is called the spectral duality relation. This is what we're calling it. And we were able to show that there's a precise analytic relation that relates the spectra in one channel to the spectra in the other channel. So again, it's done with the help of some duality that looks like this at the bottom. So the correlation functions in the 2-channel are constrained by general relativity to a form that looks like this. There's some the details are not important. It's just some function that's easy to compute called the algebraically special frequency. And again, actually, the reason why we found this was because we saw that this one special function that constrains everything is again related to pole skipping. And in fact, you can kind of understand it as the places where the hydro mode goes through that I was showing you before. So this function omega squared of q is precisely this function qn that tells you where the hydro mode is as it goes through the pole skipping points. So with all this, we were able to prove the following thing. This is now a mathematical statement. So let's take a following infinite product. Yes?
So this isospectrality is valid in the fluid regime also when we calculate modes from Navier-Stokes theorem?
No, this is a statement about black hole. This is a statement about black hole perturbations. And actually, in asymptotically flat space, there's no hydro mode really there. No, so this is a purely GR statement about gravitational waves.
Okay.
I'm not aware of any meaning that isospectrality has on fluids. No, not aware of anything. Okay. So the reason why I will be able to say something about, fluid-like things is because now we have a theorem for anti-de Sitter space, which then through holography, ADS-CFT correspondence can be mapped onto a thermal field theory, which does include Hydra. Okay, that's the reason why now I can say something. So form the following infinite convergent product. So you have first here factor 1 plus omega divided by omega star of q. This is this algebraically special frequency, which is very easy to compute in gravity. This you can do. And then let's say you have an infinite product over the following. So 1 minus omega divided by omega plus n. Omega plus are all the quasi-normal modes in all the poles of the spectrum of the sound correlator. And these are all the poles in the spectrum of the shear correlator, the ones that have diffusion. So there's a minus sign and a plus sign. We can prove that this converges. So this infinite product, we could then prove using general properties of meromorphic functions. And a very important result that recently came from the CERN group around Sasha Zhibuyedov called the thermal product formula. So all these things go into it. We were able to show that this combination, so S of omega in Q minus S of minus omega in Q is universal. So this is always equal to 2 times I times lambda of Q. Lambda of Q can also be computed from the quasi-normal modes. And this entire thing, which, you see, it's an infinite product over omegas. This could be any function of omega. Who knows what this could be? But actually, the functional dependence of omega is always sinh of beta omega over 2. I think it's quite a remarkable formula, very unexpected to me. So the omega dependence is completely constrained by the sinh. There's nothing else that can ever happen. So what this actually gives you is an infinite set of constraints on the spectra. And we were able to show that the following statement follows. So if you know the diffusive spectrum, you can from that compute the sound spectrum. If you know the sound spectrum, you can from that compute the diffusive spectrum. And actually, you can see how, let's say, the diffusion constant depends, or the diffusive hydro will depend on the sound plus some properties of the ultraviolet quasi-normal modes. Okay, it's this very intricate kind of connection where all the modes on one side contribute to all the modes on the other side in very non-trivial ways, but it works. We can actually check numerically in the holographic settings that this works. So also we're able to, for example, show the following. So if you know all the poles, which are all the dispersion relation, then you can also fix all the zeros. So there's enough analytic structure in such functions that you can constrain everything. Okay, from the poles you can constrain the zeros. So then you get the correlator, and then from that you can compute the other correlator. So everything is really, really finely, tightly constrained. Now, I should say, so where is this valid? It's valid for any dual to 4D gravity or 4D electromagnetism. So in particular, this is what this is really coming from. If you never knew anything about gravity, these are three-dimensional thermal field theories, CFTs with S duality. Or in other language, this is the particle vortex duality. This is really helping you sort of constrain this. Okay, I still wouldn't know how to do this from S duality, but with the help of, because one of the problems is that from the S duality, we don't know what is the meaning of the algebraically special frequencies. It's just something that comes from gravity, even though the statement at the end is purely QFT. Okay, actually, I should also say that in some limits, this omega star goes to infinity, and then G plus G minus is equal to -1. And this is what we now call the self-dual limit. And this was explored before. So there's a very famous paper by Sachdev, Son, Koftun, other people, I think, as well, where, for example, they were able to constrain holographic thermal and electrical conductivities in three-dimensional CFTs by using this. So this is now can be understood as a special limit of our whole sort of spectral duality relation. Okay, so this works for 3D stuff. Interestingly, it also works for relating spectra in any dimensions, as long as the two theories are related by a Legendre transform. So for example, for experts, when you have a CFT with a double trace renormalization flow, you flow from ultraviolet to the infrared, we were able to show that the UV and the IR spectra also satisfy this spectral duality relation. And in fact, actually, so if you know one spectrum, so if you know the UV spectrum, you can compute the IR spectrum uniquely. Interestingly, if you know the IR spectrum, you cannot compute the UV spectrum. You need the knowledge of one more function of Q. So this smells like sort of RG. Again, in this case, made very precise. Okay, so this was the last sort of thing I wanted to show you for how extremely, these theories that have a relation to holography are constrained, and how much, hydrodynamics sort of really is able to bootstrap itself all the way to the ultraviolet to tell you all sorts of things about spectra, and as a result, also about black holes in higher dimensions. So as a little summary, classical hydro has this extremely rich structure, okay, that we've been exploring now for years. And every time I want to stop working on hydro because it feels like it's been too much, something interesting again pops up, and then again I'm sucked back into this. So in these holographic large N theories, it really allows us to, at least in principle, you can make a mathematical statement, reconstruct the entire spectrum. You can go from IR all the way to UV. So through this, we also found that these holographic large N theories and classical gravity are extremely constrained. And the most stringent of such constraints is this spectral duality relation, which we recently developed with Miele. And now, the outstanding questions are sort of clear. We really need to go beyond this large N of holography, go beyond large N of field theories, which in turn will also allow us to go beyond classical hydro. Now, not that much in our community is known about not classical hydro, really not much beyond what I told you. So when you have an EFT and you can compute these loops and you get some certain predictions about this. So I think there's a huge number of things that should be explored there. And with these EFT techniques, we really now have the tools to do this. Doing this from holography is much, much harder because these corrections are encoded in essentially quantum gravity loops. And doing quantum gravity is not particularly easy. Some very, 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 very few things have been done, but it was more sort of post-dictions of things that people already kind of assumed had to come out, like long time tails. So that has been seen. But it would be really interesting to go beyond this. And I think that maybe in this case, like this, non-classical hydro can actually help us develop some intuitions about how quantum gravity should work. Maybe one can say something going the other way. I don't know. But this is certainly a sort of a massive field of open questions. Okay, thank you very much.
Thank you very much. So questions?
I'm sorry, I was a bit long.
It's okay. Can I start with questions? A question. Right. So I guess when you derive this duality relation, you would use maybe if you want to prove it from CFT, you want to use large N expansion or something. Is that correct?
Yeah, it's correct.
Is there any way you can do it at large temperature or something? Because
I don't know.
I see. Because when you go to large temperature, you see you reduce a thermal cycle to be very small, so you have an effective field theory, and that's what I was hoping. But,
yeah, I agree. So what are these algebraically special frequencies in thermal field theory or thermal CFT? I would love to see. This is unknown. So in this middle paper, this PRD, we have some statement from the gravity, from the boundary, but it's in terms of Weil tensors and cotton tensors, and I mean, it tells me nothing about the CFT that I would want to know. So for me, maybe in this spectral duality relation, this is the most important open problem. How do you see this from CFT? Yeah, and it should have something to do with particle vortex duality and the large N. Yeah, maybe it's true beyond large N. That I don't know, but yeah,
I understand.
Yeah. So it's a big open problem. I don't know. It's something that I think about, but I haven't really done anything about it. Yeah, thanks. It's a very important point. Yeah.
Thank you.
So I have another question. So towards the beginning, you showed some results like you could multiply the same factor, like same function in the numerator as well as the denominator. Yeah, here
Do
and
you see
you could,
this?
yeah,
Yeah,
and you could change the spectrum of your modes here, right?
that's right.
So could you tell me if there are any particular constraints or any properties that these functions should satisfy, the ones which you multiply in both the numerator and the denominator?
No, actually, you can. So if you let's say you want to work with, I don't know, fifth order hydrodynamics, what it means is that you can. So this B and A will both be, let's say, fifth order polynomials in omega and Q. Now you can take this and you can multiply it with any polynomial, and then so the product of the numerator has to now be truncated at fifth order, and the product of the denominator has to be truncated at fifth order. So they look very strange. They don't look like they came from the same thing, and they have very different meanings, right? So the poles which you sort of shifted around and added. So yeah, exactly. So you can just no. There's no constraint on this P. It can be anything, and so there's always a set of transformations, of these frame and on-shell transformations, which will bring you to some set of new modes. Yeah, because now you have this polynomial. So you'll have So there will be basically what happens is the following. So you have one real solution, which is the gapless one. Gapless meaning that when Q is 0, omega is 0. And then you'll have, depending on the order, you'll have more and more and more these spurious gapped solutions. They all have the property that when Q is 0, omega is not 0. And you can arrange them sort of, I think, wherever you like, in such a way so that your code will be stabilized, basically. I think this is really what all of this frame transformation comes down to. And there's such a huge amount of freedom. And then all of these things are basically the same hydro theory. So the gap modes are arbitrary, but this nilpotent Lie group has some group invariants. And for example, the most important group invariant is the dispersion relation of the gapless mode, of the hydro mode. So no matter what you do, you cannot change that. So that we were now able to show algebraically using group theory. It's like this. So actually, if you're interested and you look at the paper, the last section of the paper is just doing diffusion. So we just show, in the case of diffusion, how this works. It's very explicit. You can just add stuff.
Yeah. So in one of our recent works, we tried to do something similar, and we suppose if we started with a stable causal theory, we could remove some of the non-hydro modes using this kind of a procedure, like doing some field redefinitions. So I was curious if in stable causal theories, like say Israel-Stewart or the BDNK, like what could be the group theoretic invariants there? Like, is it only the dispersion polynomial, or could there be something else as well?
There are more. There are more. We found some that was kind of nice, but for example, one I think where you're going, and which is also what I agree with, is it would be great to, at the end of the day, just write hydro in terms of these group invariants, so that then everything is kind of nice and physical. This we have not explored to sufficient amount. I don't see who I'm actually speaking to, but are these maybe the papers with Sayantani? Is that what
Yes.
we're talking about?
Yes.
Aha. So this were real. I see nothing. So these were very close. I spoke to Sayantani about this, of course, in Edinburgh. So I think the one difference between what you guys were doing and what we're doing is you were not truncating sort of so rigorously at So there's a really a differences in how we sort of we multiply, and then we really have this truncation operator that so that at no point when you introduce higher, at no point when you change the frame, you go to a higher order hydro. You always cut off to where you started with at the same order. So I think that's something that's different in our approach and yours. But yeah, otherwise, of course, this is all very related. Yeah. I think we should talk more in somewhere in the world. Who knows in what formation?
Maybe one last question.
Yeah. Great talk, Saso. This is Gautam
Thank
Mandal
you.
here. Yeah, so
Okay. Now I actually see you. Yes.
So this is about the cuts becoming poles. So it just reminds me of Wheaton's large N baryon paper, where he showed that if you look at the current correlator, you have generally this fishnet diagram, which connects the two currents. And typically you'd think of a very complicated structure of cuts because there are so many, intermediate quarks. But what he argued was that, you can only have in the dominant channel in the large N limit, the dominant channel is a singlet channel. And therefore it, picks up the meson poles. So instead of the cuts, just because of the large N argument, so it seems to be rather, what I mean is that it's a very robust argument. And in case of the, Grozdanov model, you can actually show it that in the singlet channel, it just is that meson that comes about. So I'm just wondering whether even without holography, just from the point of view of the effective field theory, just by using large N somehow, one could show that it certainly happens in large N QCD. That's what I'm saying.
Yeah, I mean, look, this would be great. I'm actually, Which paper is this by Witten?
This is the old paper of Witten called Large N Baryons, where he has the discussion of baryons, of course, in the second half of the paper. But in the first half of the paper, he shows how the meson poles or the glue balls. In fact, in our case, because you are doing holography, I think glue balls would be the more appropriate things to say because
yes, yeah, exactly.
That will be the gravity modes. In that paper, this is absolutely beautiful argument that you cut through this fishnet, and just by demanding that whatever you are cutting through has to form a gauge invariant singlet, picks out only one propagating particle, a singlet. That's a meson. And
that's very nice.
Yeah.
Okay, great. Yeah, no, actually, I will look at this. I've not read this paper. I will look at it. It sounds very relevant. So, and then I think the question that still really remains is, what is reality at finite N? I mean, let's say, so somehow, always perturbatively, you find cuts. And then I don't know, I mean, is there maybe sometimes, can they resum to a poles again? Can they dissolve? Was his argument that for any N that's not infinite?
No. I think at leading order in the 1/n corrections, I don't think he could have said that there are some perturbative theory of the poles.
I see.
No, sorry. I take this back. No, he did show that it becomes a theory of interacting mesons in which you have the meson interaction. But then it would be a cuts coming from the interacting meson theory. No, I think he would say there are cuts at subleading orders.
I see. Yeah. Okay. So I mean, but these are exactly the types of questions that I would just sort of like to understand for generic. Here we're talking about energy correlators in thermal field theory. So, but this is very relevant. This type of thinking. Yeah, exactly. I cannot say more than what you just said, except that it is relevant. Yeah, absolutely.
Thank you.
Thank you.
So let's think Saso again.